Okay, so good morning to everyone who's here. If someone can confirm that you can hear me. Okay, it looks like you can hear me, so that's all good. So this is really our first tutorial session, and to be honest, in this environment, I'm not quite sure how well it's going to work. So let's see how it goes. I have requested that the tutors be set up as part of the module. So it's quite possible that from next week, one of the tutors would be running a session like this. So for now, I'll start with a few announcements and then we'll switch over and do some problems or look at some of your questions. Okay, so the first one is I'm still battling with the software that I was planning to use for recording your lectures. So for this week, for tomorrow evening, we will do the lecture like we did on Tuesday. Obviously, you don't have to attend because the recording will be there for you to access afterwards. I do have to get the software. I do have to get to a point where I can record lectures and load them so that I don't have to be there physically, because in 2 weeks' time, I will have a clash for the Tuesday lecture. So that's the one thing I needed to say. The second thing is we were asked by the Faculty of Science to not have any assignments that count towards your mark, your exam mark or your final mark for the module within the first 2 weeks. That email came through yesterday, which means my plan of making your first web work assignment to open today has now been postponed. I'll open it on Monday, right? What I might do is to do a separate web work exercise set for this week. So I'll open it in the next few days and then give you until Sunday, and that one will be a practice session for you to see that you can log into web work, but we definitely won't use the mark for that first one. Okay, so your first web work assignment that counts towards your mark, your exam or semester mark, will open on Monday. Okay, that's all the admin stuff taken care of. One more thing. I had a request from one student that I should make the solutions available earlier. So what I'm going to do is I'm going to try and make the solutions for old tutorial problems for the previous available for the previous week. So sometime in the next day or two, I'll post the solutions for the problems from tutorial 1, and next week around this time I'll post the solutions for tutorial 2. Tutorial 2 was just loaded about an hour ago, so it's there. Please download it and start working. It covers 11.2. Okay, and that, as far as I can tell, covers all the admin issues. So let's talk about what it is that you find challenging. Type your question if you can. If you do need to talk, then raise your hand, unmute yourself, ask the question, and then mute your microphone again. Okay, it's over to you. I'm watching what you're typing and listening to what you say. Okay, no questions. Paho, your hand is up. Please ask your question. I think it's Mr. Paho, right? Mr. Powell, feel
Okay.
free to ask your question.
Okay. Hello, sir. Can you hear me?
Yes, I can hear you. Go for it.
Okay. Sir, I was trying to go through that proof of upper bounds and lower bounds. So I do not understand it. Can you please help me
Okay,
with?
so yeah, I'm listening. I just want to open the notes while you talk. I'm listening.
Yeah, like it's kind of confusing me, especially when we introduce E and N, and the next thing L minus E. The next it confuses me. The more we keep on putting more variables to prove it.
Okay, in the lecture notes, I'm opening the lecture notes now. In the lecture notes, can you tell me exactly what the proof is called? Okay, so I think I'm looking at the comments now. Please provide examples for greatest lower bound, upper bound, and least upper bound. Okay. Okay, so that's the first one. So I think this relates to with what Mr. Powell was asking. Greatest lower bound, least upper bound. Okay, so what I'm going to do is I'm going to open the slides and go to that part. Let me see if we can re-explain that. Okay, I'm going to share my screen. So the first thing I'm going to do is I'm going to talk about greatest lower bound, least upper bound, and then we talk about that theorem. So there DP Pillay asks about example 14. I still need to do that example in detail, right? So I haven't spent time on that. I was going to record a video for you. Let's start with the greatest lower bound and least upper bound. Okay, almost there. Almost there. Okay, so there you should be able to see definition 11 now, right? So to understand the concept of a greatest lower bound and a least upper bound, we first need to understand the concepts of bounded above and bounded below. So this definition starts there. It says a sequence, AN, is bounded above if there is a number, capital M, such that AN is less than or equal to M for all N greater than or equal to 1, right? So in other words, what this is saying is this number, capital M, the sequence can never grow bigger than that. Even if you go to the millionth entry in the sequence will never be larger than capital M. And so because every element of the sequence, every value that the sequence reaches is less than or equal to capital M, we call capital M an upper bound, right? And we say the sequence is bounded above. M is an upper bound. In a similar way, if a sequence, if there's a number that is such that all elements in the sequence are greater than or equal to that number. Now I'm using the symbol lowercase m, right? Then that sequence is said to be bounded below. And we say that little m, lowercase m, is a lower bound. If a sequence is bounded above and it's bounded below, then it's a bounded sequence. So now, instead of just having this concept available for a sequence, which is a function, we can have it available for an arbitrary set. And so a set, a subset of the real line, can also be bounded above and bounded below. So look at that set. Remember what that set represents. That set represents the set of numbers in between 0 and 1, including 0, but not including 1. So in that set are numbers like a half, right? 3/4, 1/4, 1 divided by 10, 0. 0 is also an element of that set. But numbers that are not in that set, I'll give you some examples. The number 2 is not in there. The number 1.5 is not in there. So now for that set, I'm going to give you an example of an upper bound for that set. An upper bound for this set is the number 1. Because any number in that set S is less than or equal to 1. Let's see. Remember, we define a term, then that definition gives us the pattern against which to measure that concept, right? So let's go back and look at what we mean by bounded above. So there's the definition in front of you. Now I'm applying the definition not only to a sequence, I'm applying it to an arbitrary set because the concept is the same. A sequence is bounded above if every element in the sequence is less than or equal to m. Now let's see if 1 satisfies that condition for the set S. Here we go. Yes, any element in that set S is less than or equal to 1. Yes, so 1 is an upper bound for the set. But let's look at some more examples. I mean, look at the number 1.5. Now 1 is less than 1.5, which means if any number is less than or equal to 1, then it must be less than or equal to 1.5. And you see that, which means if 1 is an upper bound, then 1.5 is an upper bound. Similarly, the number 0 is a lower bound for that set because any element in the set is greater than or equal to 0. But -1 is also a lower bound for the set, and -10 and -100. Because if any number is bigger or equal to 0, then it's bigger or equal to -1 and -0.5 and -100 and -1,000, right? So when you read this stuff, you must always go back to the definition and see that it makes sense, right? So there I'm saying 1 is an upper bound of S, but 1.5 and 2 are as well. Okay, now I'm going to skip forward to the least upper bound bit. So now you know you need to first understand what it means for something to be an upper bound. Now, Now we're going to introduce this new thing called a least upper bound. Now I've got a set again, the set S, a subset of the real numbers. An element M0, a real number, is called a least. I'm going to look at the comments in a minute. I'm still answering the first question. So keep them coming, but you'll have to wait. Let S be a subset of R. An element M0, a real number, is called a least upper bound of the set S if it satisfies two conditions. Number one, M0 must be an upper bound of S. And number two, if M is any upper bound of S, then M0 must be less than or equal to M. That means M is a least upper bound. In other words, of all the upper bounds, M0 is the smallest one, the least one. So go back to this example again. This is 0, 1, this interval, open on the one side, closed on the other side. We saw that 1 is an upper bound for the set. We saw that 1.5 is an upper bound. We saw that 3 is an upper bound, 1,000,000 is an upper bound. So this set has an infinite number of upper bounds. Right? Now you can see that a half is not an upper bound. How do I know that a half is not an upper bound? Well, I can find a number in that set, 3/4, which is bigger than a half, and so a half cannot be an upper bound, because for a half to be an upper bound, every element in S must be less than or equal to a half. That's the definition. So now I can have a similar way. You can go through the reasoning step by step. Any number that's less than 1, and I prove it in the notes, any number that's less than 1 cannot be an upper bound for the set. And because of that, the number 1 is the least upper bound for the set. In a similar way, when you go through the concept of greatest lower bound, the number 0 will turn out to be the greatest lower bound. It's a lower bound, and any other lower bound for that set will be less than or equal to. So 0 is the greatest, it's the biggest of all the lower bounds of the set. Now this is important because this concept allows us to prove our first theorem, right? The first theorem. But before we can do it, the reason we introduce it is because we need this thing called the completeness axiom of the real line. And it says, or the least upper bound property of the real line, and it says, every non-empty set of real numbers that is bounded above has a least upper bound, right? And if we accept that, and we are happy with that, then by interchanging the role of greatest lower bound and least upper bound, we are also able to prove that every non-empty set of real numbers that is bounded below has a greatest lower bound. And with that, we can prove this theorem, that every bounded monotonic sequence is convergent. And here's the proof. Okay, before we continue, let me have a look at your comments and questions, and let's see how to go forward. Okay, there's quite a few new things. Okay, Mokhwame, I've just done that. Okay, I've just provided examples of greatest lower bound and least upper bound. Struggling with 29, explain example 14, general formula. Okay, Ms. Opperman, we'll come back to that one. The concept of M in the bounded situation. Okay, done that. Number 14. Previous recordings via BC. Okay. Okay, that looks like it's a different conversation there. Okay, cool. Okay, so I think we're all good now. Are we all happy with greatest lower bound and least upper bound? Can I move on to something else? Okay, Hlongwani says yes. Let's look at Ms. Opperman's question. There's a question from Ms. Opperman about one of the questions. Okay, for tutorial 1, question 83, where should we start with deriving or showing how Fibonacci created his formula? I have worked out what the sequence is, but I do not understand how to answer the question. Okay, let me open up my textbook. I have a PDF of the textbook, so let's open it. I'll go to that question and then we can share it. And I can share it and we have a look at, and that's question 83, I think you said. 11.1. Okay, can I come back? Okay, there's a question by Pillay that I want to answer quickly. DP Pillay asks, M0, sir, is it referring to the value of M at 0? No, DP Pillay. It is a particular value of M. It uses a new variable for which we can still use the symbol M for, right? But it refers to a particular other value which we also denote by M, but it's not the old M, it's a new M. So it's not M at 0. No, go read it again. Okay. Okay, I'm going to share my screen and we look at question 83 and we see if we can answer Ms. Opperman's question, and basically she wants to know how do we get started. So the question says, Fibonacci posed the following problem. Suppose that rabbits live forever and that every month each pair produces a new pair which becomes productive at age 2 months. If we start with one newborn pair, how many pairs of rabbits will we have in the nth month? Show that the answer is Fn, where Fn is the Fibonacci sequence defined in example 3c. Right? So let's look at 83a. So you want to know, how do you get started with this? So let's look at the first few Fibonacci numbers. So the first one is 1, then it's 1 again, then it's 2, then it's 2 plus 1, it's 3, then it's 2 plus 3 is 5. Let's go up to 5. So now, the way to do this is do it for the first few, maybe go up to 8. Do it for the first few numbers. So let's look at what they describe here. Fibonacci posed the following problem. Suppose that rabbits live forever, right? So in other words, if you think about that, even if we are talking about 713 months from now, the rabbits that we had in the first month will still be around because they live forever. And that every month, each pair produces a new pair, which becomes productive at age 2 months. So each pair produces a new pair. If each month, each pair produces a new pair. So I would start by saying, let n be the month number, right? So n is 1, Fibonacci is 1, f1 is 1, f2 is 1 as well. So in month 1, you only have 1 rabbit. In month 2, you're adding another rabbit, right? So in month 3, you've got the sum of the first 2, which is 2. So that gives you f3 equals 2. Now you need to use the next bit of information, which becomes productive at age 2 months. Right? So now the one from month 2 the ones from month 2 become productive because they 2 months old, right? And they produce, no, it doesn't look like it's going to work. Suppose that rabbits live forever, and each pair produces a new pair, which becomes productive at age 2 months. If we start with one newborn pair, how many pairs of rabbits will we have in the nth month? Okay, so the number 1 is a pair, right? So 1 refers to, so each Fibonacci number refers to a pair of numbers, right? I just want to have a look at the notes again. So just give me a second. Sorry, let me stop sharing for a minute. And let me mute myself for a second. Okay, let us get back to it. So for us, we're going to say that Fibonacci n, where n is the, so let n be the number of months, right? Let m be the number of months. Then if n is equal to 1, whatever the month number is, Fn is the number of pairs, right? So where Fibonacci 1 is 1, it represents a pair of rabbits. So you know that Fibonacci 1 is 1, Fibonacci 2 is 1 as well. Fibonacci 3 is 1 plus 1, which is 2. Fibonacci 4 is 1 plus 3, which is, 1 plus 2, which is 3. Okay, so that means F1 is 1, which is F2, that's fine. So in the nth month, each pair that is 2 months or more old, right? Now, how many pairs will that be? So it must be 2 months or so old, 2 months old, right? Or older. So that means if n minus 2, that's the number of rabbits that will be old enough to pair, right? So that's Fn minus 2. And they will produce a new pair to add to the Fn minus 1 pairs already. So look at point n in the sequence, right? At that point, the number of rabbits F is represented by Fn, right? So now, in the beginning of that nth month, how many rabbits do we have already? Well, we had what we had from the previous month, right? Which is Fn minus 1. And in addition to that, the new rabbits that are created by the pairing of the ones who are 2 months old, right? Who've just become able to create, which is plus Fn minus 2. And there you go. You've now established the fact that Fn is equal to Fn minus 1 plus Fn minus 2, which is the Fibonacci formula. Okay, so still have a go at it on your own a bit later today or tomorrow. So I'm answering Mokwame's question, right? So are you able to write it down? I'm starting to follow through for question 83. So my answer to that is in the next couple of hours or by tomorrow, the latest, I'll post the solutions for the questions from last week, right? And so you will see how it's written out, okay? So, Ms. Opperman, I've also left B still for you. So now that you've seen how I've sort of reasoned through 83A, see if you can look at B on your own, okay? It's important that you do them on your own as well. Okay, so shall we look at another question? We've got about 10 minutes left and then we'll take a break and we'll do another 45-minute session. More questions? I thought there were some really nice ones in the tutorial. I want to open up my electronic copy of the textbook, because then we can have a look at some of the ones that are there, and maybe, okay, so I've got it open now. Now I must just go to chapter 11. And to make this a little bit bigger. Okay, now I'm going to share. Since everyone is quiet, I'm going to share my screen, and we look at some of the questions. So there's 11.1, right? So there's one that comes to mind immediately, that one student sent me an email about 37. So look at 37, right? The question wants to know whether it converges or diverges. If it converges, find the limit. So 37, look at 37. So now remember what the factorial function is. The factorial function is multiplying numbers that you start with 2n minus 1, then go to, what's the next one down? It'll be 2n minus 2, right? 2n minus 3, all the way down to 1. That's the numerator. Now look at the denominator. 2n plus 1. What's the one just below that? That's going to be 2n. And then the next one is 2n minus 1. So now 2n minus 2 and so on, all the way down to 1. So if you think about this carefully, you can cancel the 2n minus 1 factorial with 2n minus 1 factorial in the denominator. Then you'll be left with an expression that has no n's in the numerator. And if n goes to infinity, then that expression, well, I've given you some hints there. See if you can tackle that one. 45 is a nice one. 45, I've had a few emails around 45, so I'll give you a hint for that one. For 45, you cannot use the limit laws. You cannot use it because there we've got the product of two sequences, right? So the one sequence you can think of as a sequence which is n. So you could say there that an is equal to bn times cn, where the bn is equal to n. And the cn is sine of 1 over n. Now, that bn is not a convergent sequence. Bn is 1, 2, 3, 4, and so on. It gets larger. It doesn't converge to anything. Now that means we cannot use the limit laws for sequences, because the limit laws for sequences only work if both in the case of the product, it only works if the individual sequences converge. Go have a look at the conditions, which means you need to think about this slightly differently. So think about the n times sine 1 over n. Rewrite it as sine 1 over n divided by 1 over n. And then you need to go and look at something you did in the 1a module. In section 3.3, when we were discussing the derivatives for trigonometric functions, we proved two special limits. And one of them is the one relating to the sine function. When you go and look at that, you'll see that the form of that limit reminds you of this. Okay, so there's another hint. Anything else there that comes to mind? I'm going to stop sharing and look at your comments. Question 29, someone says. Okay, let's have a look at 29. Let's have a look at 29 quickly. And maybe we can stop after that. No, we've still got 3 minutes. 29. Okay, 29 is also an interesting one. Okay, so now let's see how we would tackle this. So I want you to keep 29 in mind. I'm going to scroll with these in these notes, the textbook notes, because there's a theorem you need to use for this, and I don't want to open up a new set of notes, right? The typed notes. I'll just give you this. I'll just go look for the theorem. Yeah. Come on. This is so slow. There's the theorem. Theorem 7 says, if the limit as n goes to infinity of a n is L, and the function is continuous at L, then the limit as n goes to infinity of f of a n is f of L. Now, when you look at this, I mentioned this in the lecture. When you look at this, remember that L, look at the L inside the bracket of the f on the right-hand side now. That L is the limit as n goes to infinity of a n. So if you replace the L, what you have is the fact that if a function is continuous at the limit of a sequence, then you can interchange the limit. You can take the limit from outside the function to inside the argument of the function. That's what the theorem is saying. So now let's go back and look at 29 again. And I'll give you a hint for tackling 29. And this is so slow. No, this is too far now. Here we go. There's 29. Okay, so now here's what you're going to do. You're going to remember that the exponential function with base e is the inverse of the logarithmic function. And you're going to say something like this. A(n) equals e to the negative 1 divided by the square root of n. You'll write it out as an equation, right? Then you're going to apply the ln function on both sides. So you'll say ln of an, the logarithmic function with natural base. Ln an is ln of e to the negative 1 over square root n, right? And because ln and the exponential function are inverse functions, on the right-hand side, you're going to get the expression negative 1 over the square root of n. Then you're going to take the limit. The limit of ln an is going to be the limit of that expression. You're going to get an answer. Then you're going to use the theorem I just showed you, theorem 7, right? And calculate the actual answer that you want. Because remember, when you take the limit of ln an, it's not the limit you want, right? You want the limit of an as n goes to infinity. Okay, so there's a nice hint for that one. Okay, let's take a break. And let's say it is now 10:27. Let's start again at 10:35, right? I'll schedule a new session for 10:35, and I'll have a look at the questions that were posted after that. And then we pick up again at 10:35. Okay, cool. See you in